Can you see the slide?
Yes, sir. Now it's perfectly
Okay,
visible.
okay, fine, fine.
Yes, sir.
So we were discussing how to do the input-output modeling using statistical regression analysis and some non-traditional tool for this input-output modeling using the concept of fuzzy sets and fuzzy logic. And in the last lecture, I also discussed about the feed-forward neural network and using the feed-forward network, how to tackle the problem related to input-output modeling of a process. Okay, so let me continue this. Now I'm just going to discuss the principle of another network that is called the radial basis function network, that is RBFNN, and this particular network can also be used for this input-output modeling. Now let me try to find out the basic difference between the multi-layered feed-forward network and this radial basis function network. Now, if you remember, the multi-layered feed-forward network, which I discussed in the last class, that is nothing but a three-layered network. Now, this radial basis function network is a two-layered network. Okay, you can see that we have got the input nodes, but not the input layer. Okay, and you can see that here I have used a different types of small filled up circles in place of this type of bigger circle, the blank bigger circle. Okay, now there is a difference between so this type of notation of the circle and that type of notation of the circle. Okay, now here in a radial basis function network, in place of input layer, we pass all the input through this input node. Okay, that is directly the dimension wise, that means all the inputs I'm going to pass through this particular the nodes, and supposing that I have got capital M number of inputs of a process and there are capital P number of outputs of that particular process, and I'm just going to carry out the input output modeling. Okay, now if you compare the multi-layered feed-forward network and this radial basis function network, there are two basic differences. Like in terms of computational complexity, if you see, so this particular network is faster compared to your multi-layered feed-forward network. But in terms of accuracy, if you see, so this network could be slightly worse compared to your multi-layered feed-forward network. Now, construction-wise, on this hidden layer, that is practically the first layer, we use some radial basis function as the transfer function. Now, let me try to define this radial basis function. So, by the term radial basis function, we mean a function which increases or decreases monotonically, okay, with the value of x. That type of function is known as the radial basis function. Now, there are many such radial basis functions, and out of all such functions, the most popular one is the Gaussian distribution. I hope all of you know about this Gaussian distribution. And the Gaussian distribution is having the mathematical expression like y equals to e raised to the power minus half x minus mu divided by sigma square. Okay, let me repeat. Y equals to e raised to the power half x minus mu by sigma square. Mu is nothing but the mean, and standard, and sigma stands for the standard deviation. Okay, so Gaussian distribution, all of you might be knowing Gaussian distribution or normal distribution. So that type of transfer function we use in the hidden layer. And on the output layer, we can use either the linear transfer function or some nonlinear transfer function can also be used. Now, the way it works is as follows. We pass all the training scenarios one at a time. So corresponding to a particular training scenario, so I'm going to pass all the inputs, okay, like your I1, I2, II, and IM. So there are M number of inputs here. Okay, and here we do not use a variable connecting weight here. So what we do is whatever output we are getting, and output is nothing but the input in the real scale, not in the normalized scale. So this is the difference between the radial basis function network and multi-layered feed-forward network. Here the inputs are passed into in their real forms. Like one of the inputs could be 5.78 or 16.58 or and so on. So there is no such restriction that the inputs has to be in the normalized scale like 0 to 1 or from -1 to +1. Okay. So the inputs in the real scale we pass, output is nothing but the inputs here, and all such inputs are summed up here as the input of your the hidden layer. Now, if I do like this, the input of all the hidden layers will be equal numerically. That means the numerical values of all the inputs will be equal. Now, here we use Gaussian distribution of different means and standard deviation. Okay, so corresponding to this particular first hidden neuron, we have got one set of mean and standard deviation. Corresponding to the jth hidden neuron, another set of mean and standard deviation. Corresponding to the nth hidden neuron, another set of mean and standard deviation. Now, depending on the mean and standard deviation of the Gaussian distribution, I will be getting the different outputs. Okay. Now, this HOJ is nothing but the output of the jth neuron lying on the hidden layer. So, similarly, you can find out the output of all the hidden neurons. Okay. And once you've got the output, you can multiply by the connecting weight. You sum them up and you'll be getting the input of the output layer, and then it will pass through the transfer function and you'll be getting this particular output. So on the output layer, you'll be getting all the outputs here. Okay. And once you've calculated all the outputs, now it can be compared with the target value. You can find out the error, and this error will be propagated back using the back propagation algorithm or any other nature inspired optimization algorithm like genetic algorithm and others. And we'll be able to find out what should be the updated or the optimized values for this connecting weight and the mean and standard deviation of the different hidden neurons. Okay. And once it is trained with the help of some training scenarios and some optimization algorithm, now we can pass the test scenario. And if I pass the test scenario, that is the inputs of the test scenario, so you'll be getting that particular output. And this output will be compared with the target, and error is determined. And that particular error will be fed back if you use back propagation algorithm and if you use genetic algorithm and some other nature inspired optimization tool. So this error will help you to find out what could be the fitness value. So this is the way actually we can do input output modeling using your radial basis function network. Now I'm just going to concentrate on another very efficient network that is called the recurrent neural network. Now, to understand the purpose of using recurrent network, I want to explain with the help of a very practical example. Okay, so all of you do not look into the slide, but you try to imagine a physical problem of turning carried out on a lathe. Okay, that means the turning operation carried out on a lathe, the same example which I took yesterday. Okay, so I want to find out a very good surface finish on the turned part, the straight turning job I am doing on a lathe, and the inputs are cutting speed, feed, and depth of cut, and the output is nothing but the surface roughness of the turned surface. Okay. Now, supposing that an operator has selected cutting speed, feed, and depth of cut while doing turning. Okay. Now, remember, we select cutting speed, feed, and depth of cut on the lathe. We start that particular turning process, and after some time we'll be getting the turn product. Okay. Now the quality of that particular surface, the turn surface, depends on the input parameters that I discussed in the last class. Okay. Now I'm just going to tell you another fact. The moment we select the cutting speed, feed and depth of cut on a lathe, some internal inputs are generated, okay, depending on these external inputs like cutting speed, feed and depth of cut. What are those internal inputs? Now, depending on the cutting speed and depth of cut, there will be some sort of unbalance in the different moving components of that particular lathe. And consequently, due to this particular unbalance, there could be some vibration generated on the lathe in the different components of the lathe. And if there is any such vibration generated on the lathe, that is going to also affect the quality of the turn surface. And that is why we consider a very good rigidity of that particular machine tools before we design that particular machine tool. So although it has got a very good rigidity, but depending on the external inputs like cutting speed, feed and depth of cut, there will be some level of vibration generated in the machine during the machining. Okay, and this vibration will have some contribution towards the final output of the product. Okay, that is missing till today. Whenever we are using like your multi-layered feed-forward network or radial basis function network, so those things are not considered. But here in recurrent network, we consider those internal inputs, that is the level of vibration generated on the machine on the quality of the turn surface. And that is why, so this particular recurrent network is a more practical one, and it can capture the dynamics of a highly dynamic process. So for a highly dynamic process, so there is no way out, but you'll have to go for this recurrent neural network. Now, if you see the literature, there are some designs available. For example, one of the design is Elman network. This is very famous. Okay. So here actually what we do is we take the feedback from the hidden layer. So I am passing one set of external inputs, okay, that is denoted by IEX, that could be cutting speed, feed and depth of cut. Now, depending on these connecting weights, so I will be getting some input of the hidden layer, and the hidden layer, there will be some transfer function. So it will be getting the output of the hidden layer, the hidden layer. Now, this particular output is not directly allowed to go to the final output layer. Instead, so these outputs will be fed back as the internal input, and once again it will be joining as input to the hidden layer, and then I will be getting the final output, and that particular final output of the hidden layer will be multiplied by the corresponding weight, and we will be getting the input of the output layer. And depending on the transfer function, so you will be getting that particular, the final output. Now this final output will be compared with the target output to find out the error. And this error will be either fed back using the back propagation algorithm, or this error will be used to determine the fitness of a genetic algorithm or any other nature inspired optimization algorithm. And so that particular optimization algorithm, with the help of some training scenarios, will be able to find out the trained network. Okay. Now here there are two circuits. One is called the feed forward circuit. So this is the feed forward circuit, and this is your feedback circuit. And as you are taking the feedback, there is a possibility that you'll be able to capture the dynamics of the process more accurately. Okay. So I hope you are clear that for a highly dynamic process, the manufacturing process, is better to go for recurrent neural network to establish the input-output relationship, because here you'll be able to capture the dynamics of a process more efficiently. Now, another very popular design is the Jordan network. Okay, once again, we are passing some external input. You'll be getting the output here depending on the transfer function. Those outputs will be multiplied by the connecting weights. We'll be getting the input of the hidden layer, and depending on the transfer function, you will be getting the output of the hidden layer, and the output of the hidden layer are multiplied by the corresponding connecting weights, and you will be getting the input of the output layer, and depending on the transfer function, you will be getting the output, and this particular output will be in fact fed as internal input to the input of the hidden layer. And once again, I'll be calculating the output of the hidden layer, and that output will be multiplied by the connecting weights, and those are summed up here as the input of the output layer, and depending on the transfer function, you'll be getting the final output. So here, the feedbacks are taken from the output layer, but not from the hidden layer. So this is the difference between the Elman network and Jordan network. Now, if you see the literature, the combined thing is also available, where we take the feedback not only from the hidden layer, but also from the output layer, and those feedbacks will be fed as internal input, okay? And this will be once again coming to the input of the hidden layer, okay? And once again, it will pass to the transfer function of the hidden layer. We will be getting the output. This output will be multiplied by the corresponding connecting weights. Then you will be getting the input of the output layer, and depending on the transfer function, we will be getting the final output. And this final output, as I discussed several times, will be compared to the target output to find the error, and that particular error will be used to modify this particular the network. Okay, so this is the combined L1 and Jordan network, which can be very efficiently used to establish input-output relationship of a highly dynamic process. Now I'm coming to another network. I'm sorry because I'll have to be a little bit faster, okay? Because at least I want to give you at least some idea so that you can start thinking in this particular direction. As I told, all the mathematical expressions are available in my textbook and in my NPTEL lecture. You can refer. Those NPTEL lectures are also available on the YouTube. My lectures are available, so you can see all such mathematical expressions. Okay, but here I'm just going to discuss the basic philosophy, which may not be easily understandable from my textbook, but that I'm going to tell you. Now I'm just going to concentrate on the self-organizing map or the coherent network. Now, there are several applications of this particular self-organizing map or the coherent network. Now, remember, this particular tool, this particular network can be very efficiently used as a visualization tool. That means data can be mapped from higher dimension to lower dimension for the purpose of visualization. Okay. Now, let me take a very simple example. Supposing that I have got a data, and this particular data is related to say 10 inputs and 1 output. That is, y is a function of 10 variables, x1, x2 up to x10. Okay. So if it is a function of, if y is a function of 10 variables, so it is in 11 dimension. All of you know, if y is a function of only one variable, y equals to fx, we can draw it in 2 dimensions. If y is a function of 2 variables like x1 and x2, we can plot it in 3 dimensions. Okay. Similarly, if y is a function of 10 variables, it is in 11 dimensions. Okay. Now this 11 dimensional data, we cannot do any visualization because we human beings, we could be very intelligent, but our limit is only up to 3 dimensions. Whatever is there up to 3 dimensions, we can visualize. If the data is there in more than 3 dimensions, like 4 dimension or 5 dimension, not even a single person in the whole world can visualize data in 4 dimensions. So our limit is only up to 3 dimensions. Now a human being could be extremely intelligent, but nobody in the world can visualize more than 3 dimensions. Okay. So if it is 4 or more than 4, that particular data has to be mapped either in 2 dimensions or in 3 dimensions for the purpose of visualization. And the self-organizing map is a very efficient tool for transferring data from higher dimension to lower dimension, say 1 dimension or 2 dimension or 3 dimension for the purpose of visualization. Okay. And this is a topology preserving tool. So not only the distance between the 2 points in higher dimension it consider, but also it consider the relative position of the second point with respect to the first point. That means whether the second point is towards north with respect to the first point, or it is towards south, or it is toward east or west with respect to the first point, that is also considered in the topology preserving tool. Let me take a very simple example. Okay. Now, sitting at a particular place, you think about the nearby railway station. Okay. For example, you are now listening to my lecture. Okay. You try to concentrate on the nearest railway station. Okay. And supposing that you want to catch a train at your nearest railway station. Sitting at that particular room, you can make a plan how to go by road to the nearest railway station, because you know the topology of that particular road, that starting from here, how can I go to the railway station through a number of intermediate points and via points. You can make a plan. Now my question is, how do you remember this particular topology? You can remember the topology because your brain is having a network which is more towards the self-organizing map or the coherent network. Okay. Now I'm not going to discuss the mathematical formulation and all such things which are there in details in my textbook and NPTEL, but I'm just going to tell you the philosophy. Now there is a difference, the basic difference of this particular network and the network which we have already discussed, like the multi-layered feed-forward network or the radial basis function network or the recurrent network. Now remember, in all such networks, we consider the concept of your supervised learning. That means with the help of known input-output relationship and with the help of one optimization algorithm, we are going to train that particular network. But here, fortunately or unfortunately, you do not have the complete information of input-output training data. Okay. Now here, actually what we do is, we do not use supervised learning. We use unsupervised learning using the principle of the competition, cooperation, and updating. Okay. So we use the principle of competition, cooperation, and updating. Okay. The philosophy I'm just going to tell you in short, and details mathematical expression you'll be getting in my textbook. But let me tell you the philosophy behind this particular network. Okay. Let me once again take a very practical example. Okay. Now let me take, I think some of you, I think this particular course is only for the faculty members. Am I correct? I do not know. Anyway, if it is only for the faculty members, each of the faculty members, you have reached a particular level after fighting so much in your life, starting from your school level. Okay. So there is a lot of fighting, a lot of struggle, and through this particular struggle, you could reach this particular level and could join as a faculty member because you are the winner. Okay. So all the faculty members are winners. and that particular winners are decided using the principle of your competition. So there is a lot of competition among a large number of people, and ultimately you could become the winner, and that is why you could join as a faculty in one institute, in one department. Okay, so there is a principle of being the winner, that is through the competition. Okay, so here in this particular network, we use the similar principle of competition, and the winner will be selected. And once that particular winner has been selected, that means a particular professor working in a department in a particular institute, and he has got some teaching subjects, some subjects he is carrying out research and little bit of administrative work he is doing. Okay. Now, in terms of research, if I concentrate, then what will happen? Surrounding this particular professor, there will be a large number of PhD students, MTech students, BTech students, okay, and they will be working under the guidance of that particular the professor, okay. And while guiding those students, there will be a lot of interaction between the professor and the students, and due to this interaction, not only the students are going to learn, the teacher is also going to learn a lot. Okay. For example, I told in several occasions that I've learned so many things from my students because I've already completed 30 years of my teaching and research. So, and I can admit that I've learned many things from my students. Okay. So there will be a lot of interaction between the teacher and the student, and due to this particular interaction, both the teacher as well as the student are going to learn a lot. Okay, that is called the principle of cooperation. So the students and teachers, they are going to cooperate, and through this cooperation they are going to learn a lot, and they are also going to update their level of knowledge. Okay, so the same principle of competition, cooperation, and updating has been used in self-organizing map, and this particular coherent network or self-organizing map can be very efficiently used as a clustering tool. While discussing that fuzzy logic and fuzzy sets, I told that based on the similarity, clusters could be made. Here also, from higher dimensional data, we can just map it to the lower dimension, and based on the similarity, we can also do some clusters. You can see, now here, you can see this particular example. So this is a function, complicated test function, that is known as safest first test function. Okay. So if you see this mathematical expression, here you can see summation I equals to 1 to 4. So y is a function of 4 variables. That means that this is in 5 dimensions. So these 5 dimensional data will be mapped to 2 dimensions for the purpose of visualization. So from 5 dimension, 1000 data we generated at random on the surface of 5 dimensions, and those are mapped to 2 dimensions for the purpose of visualization using the self-organizing map. Now, depending on your the similarity, we can form the different clusters. Now, the self-organizing map has got different applications. Out of all such applications, actually, the one of the most important application is to develop the counter propagation neural network, that is CPNN, and the CPNN can also be used as a tool for input-output modeling. I'm just going to show you how to use the counter propagation neural network as a tool for input-output modeling. Okay, and remember, in counter propagation network, we use the principle of both unsupervised coherent network as well as the supervised learning, that is called gross-buck learning. Okay, so this is a network where we use the combination of unsupervised as well as supervised learning. Let us see how to design that particular network. as a tool for input-output modeling. Okay. Now, this is called full CPNN, and this full CPNN, you can see, I'm just going to model a process having small m number of inputs, that is x1, x2, xi, xm, and having the n number of outputs, that is y1, y2, yk, yn. Okay, so this input output relationship I'm just going to model using this counter propagation network. Now remember, this full CPNN consists of two input layers. Like the first input layer is going to carry the information of the X input. The second input layer is going to carry the information of Y inputs. Okay, and it has got two output layers. The first output layer is going to carry information of the X star, that is the input side, input variables, and the second output layer consists of the information of Y star, that is the output. Okay, so it consists of two inputs, two outputs, and in between we have got the hidden layer. And here on the hidden layer, actually there are a few neurons, but we try to find out who could be the winner based on the competition. Okay, now in between the input layers and the hidden layers, we use the in-star model. Okay, and in between the hidden layer and the output layer, we use the out-star model. And you can see the connecting words, that is U, between the X input and the hidden, then V is the Y input and hidden, then W is the hidden and X output, and S is nothing but the hidden and Y output. Okay, so this is the in-star model and this is the out-star model. So in the in-star model, I'm going to use unsupervised learning, and in the out-star model, I'm going to use the Grossbach supervised learning. Okay, and our aim is to establish the input-output relationship. Okay, now the in-star model has been drawn once again. You can see that you have got X inputs on the input layer, x1, x2, xi, xm, and Y inputs in the second input layer, that is y1, yk, yn, and we have got the connecting words, and this is actually your hidden layer. Okay, now here actually what we do is we try to find out the Euclidean distance between each of these particular your hidden layer and the connecting words. Okay, and we try to find out so these connecting words and those connecting words we consider, and we try to identify the winner of this hidden layer, and that particular winner will be selected just like the competition rule of self-organizing math. So you'll be getting this winner hidden neuron, and once you've got this particular winner hidden neuron, your in-star model is going to be completed. And now using that winner hidden neuron and the X star output and Y star output, we go for the out star model. So from this winner hidden neuron, the outputs, it is connected to the output layer, X star output layer and Y star output layer, and you'll have to go on updating the connecting words, that is W and S, using the principle of Grossbach learning. Once again, as I told you, the mathematical expressions are available in my textbook and NPTEL lectures. So I'm not going to discuss on the mathematical expression. Those are dealt in details there. Okay, but I'm just going to give you the philosophy so that you can start learning those things. Now, once I discussed the principle of fuzzy logic and the principle of neural network, I can make a conclusion that both fuzzy logic as well as this neural network can be used as a very efficient your input-output modeling tool. Now, the performance of fuzzy reasoning tool depends on the knowledge base, and the performance of the neural network depends on the optimal values of the connecting weights and the coefficient of transfer function. Now the problem is like how to determine the optimal knowledge base of the fuzzy reasoning tool, or how to determine the optimal values of the connecting weights and the coefficient of transfer function. And that is why the concept of soft computing came, where we consider the combined techniques, like we combine genetic algorithm with fuzzy reasoning tool, that is genetic fuzzy system, genetic algorithm with neural network, that is genetic neural system, and neurophagy system with genetic algorithm, that is called the genetic neurophagy system. Now, before I tell the philosophy of each of these particular thing individually, let me tell you the purpose of genetic fuzzy system is to evolve or design optimal design of fuzzy reasoning tool which can perform this input output modeling very accurately. Similarly, the performance of genetic neural system is to evolve a neural network which could perform the input output modeling as accurately as possible. Okay, and the purpose of genetic neurophagy system is actually to evolve a fuzzy reasoning tool represented using the structure of a neural network, and it is evolved with the help of a genetic algorithm. But this is basically a fuzzy reasoning tool. So with the help of this neural structure and genetic algorithm, so it will try to evolve that particular fuzzy reasoning tool, which will be able to establish the input-output relationship as accurately as possible. I think you got the philosophy, okay, behind the soft computing tools or the combined tools. Okay, now how to implement? Let me tell you in short, but in detailed description and everything you'll be getting in the NPTEL and my textbook. Now, genetic algorithm, you might have heard that it is one of the most popular non-traditional tools for optimization, and it is a population based approach, okay, and it does not require the gradient information of the objective function. This is a direct search algorithm. That means it considers the values of the objective function as the fitness of the solutions. Okay, so it starts with a population of solutions, and we consider generation equals to 0, and this population of solution will be selected at random, and we try to find out the fitness values for the population of solution, and this fitness value is nothing but the value of the objective function. Okay, and once you've got the fitness information of the whole population, now we take the help of some operators like reproduction, crossover, and mutation, and the population of solutions will be modified through a large number of generation or iteration. And ultimately, genetic algorithm is going to find the optimal solutions for that particular the problem. Okay, so I am not going to discuss in details. All such details are available in my textbook and NPTELs. Okay, but I'm just going to tell you the philosophy behind that. Now, the genetic fuzzy system, as I told, the purpose of genetic fuzzy system is to design and develop the optimal knowledge base, that is nothing but the database and rule base of the fuzzy reasoning tool, and we use one genetic algorithm to determine what could be the optimal membership function distribution of the input and output variables, that is nothing but the database and the associated rule base, so that the fuzzy logic controller can make the input output relationship as accurately as possible. Now, this training process is computationally expensive, and that is why the training is conducted offline. Okay, and once it is trained with the help of say genetic algorithm and with the help of your known input output relationship, that is the training scenarios, now the fuzzy logic controller will be getting the optimal knowledge base, and this particular knowledge base can be used to model the input-output relationship. Now, inside that particular coding of the genetic algorithm string, so all the properties related to database and rule base will be encoded, and GA through a large number of iterations will try to indicate that particular database and rule base which corresponds to a very good accuracy in input-output relationship. Okay, so this is in short the principle of genetic fuzzy system, or details are available in my book. Then comes your genetic neural system. As you know, the performance of a neural network depends on so many parameters. For example, it depends on the connecting weights, it depends on the coefficient of the transfer function. Now, what we do is in the genetic algorithm string, we carry out all such information related to the connecting weights, then coefficient of transfer function. That means, like if you see one genetic string, so this is one by the string of a binary coded GA. A few bits will be used to represent the connecting weights V11. So another connecting weight, another connecting weight, another connecting weight, coefficient of transfer function. That means a particular GA string is going to carry information of the whole neural network. Okay. Now GA, the population of solution will be generated at random. That means a large number of neural networks will be generated at random. Okay. Now I'll be passing all such training scenarios one after another, and you'll be getting that the fitness. That is nothing but error in prediction. Okay. Now this particular fitness will be minimized. That means we'll be getting the neural network corresponding to the minimum error, and that is the basic philosophy of your genetic neural system. Now, whatever I discussed, the same thing I have discussed with the help of this flowchart, like the genetic neural system. So I am not going to spend much time on this. Then comes the neurophagy system. As I told, the neurophagy system is basically a fuzzy reasoning tool, and it is expressed using the structure of a neural network. You can see that this is nothing but the Mamdani approach of fuzzy reasoning tool. So this is the input layer. Here there will be fuzzification. Are you getting my point? After fuzzification, so you'll be getting the output here. Okay. Then this layer 3 shows all the combination of the rules. Okay. And depending on the set of the inputs, a few out of these 12 rules will be activated. And depending on the activated rule, some output will be getting, and then we'll be going for defuzzification, and you'll be getting the crisp output. So this particular network is nothing but a Mamdani approach of fuzzy reasoning tool, but it is expressed in terms of neural network so that very easily you can implement the principle of backpropagation algorithm. Okay, so that is the purpose of the neurophagy system, and once again, this can be used as a very efficient tool for input-output modeling. For example, here there are 2 inputs and 1 output. Now you train this particular network, ultimately you'll be getting a very efficient and trained in the neurophagy system that is nothing but the fuzzy reasoning tool. And once you get it, you can find out the input-output relationship very accurately. Okay. And I've already discussed the Takagi and Sugane's approach of fuzzy reasoning tool. Now, this particular neurophagy system is designed based on the Takagi and Sugane's approach. Okay. So this is basically a Takagi and Sugane's approach of fuzzy reasoning tool, but expressed with the help of the structure of neural network. Okay. And then it will be trained either using backpropagation, or you can use some genetic algorithm sort of thing, algorithm, to find out this input-output relationship as accurately as possible. Let me spend some time so that all of you can understand a little bit. And this is known as the ANFIS architecture, that is your adaptive neurophagy inference system architecture. Okay. Now here the way it works, the inputs are passed to the input layer, and depending on the membership function distribution, you'll be getting the output. Okay. The mu value or the membership function value you'll be getting as output, and this shows all the combination of the rules. Okay. And this W is nothing but the firing strength of the rules. And the fourth layer is a layer of normalized firing strength. Okay. So we consider the normalized firing strength and the output for a set of inputs, and then we multiply here in this layer, that is layer 5, and those things are summed up in layer 6 to get the output. So for a set of inputs, you can find out the output. Okay. Now this output will be compared to the target output, error will be determined, and based on this particular error, so you are going to modify this particular network. And once it is trained, then it is able to make input-output relationship very accurately. Okay. Now very quickly, I'll be going for some applications. Okay. I'll not be taking much time. So I'm just going to show you some application in the field of robotics, which we did long back. Say this is a robot, that is two-wheeled one-caster robot. Okay. So this is the planning robot, and in this workspace, there are a few moving obstacles. This is the starting point of the robot, and this is the goal. Obstacles are moving, robot is also moving, and the robot will try to find out a collision-free time optimal path so that it can reach this particular the goal. This is known as the motion planning problem in robotics. Okay. So we solved using the principle of this type of network. So this type of network, that is adaptive motion planner, using this neurophagy approach. Okay. So we could use the neurophagy approach like this. We could also use the neurophagy approach like this to solve this particular problem. So this is the Mandani approach sort of thing, and this is the Takagi and Sugena's approach sort of thing. So there are two inputs, distance and angle, and two outputs, that is the deviation of the robot, so that it can avoid collision with the moving obstacle, and acceleration of the robot. That means the speed with which it should move after avoiding the collision to reach the goal in minimum time. Okay. So here also we consider two inputs, two output, and here also we consider two inputs and two outputs, and we could implement on the real robot. So this is the two-wheeled one-caster robot. Okay. And we could successfully implement this particular algorithm on this particular robot and carried out lot of experiments. Okay. Now, as I told, that might be we were the first from India to start working in the year 2000 on input-output modeling in manufacturing processes. And I remember we started with the grinding process. Like long back in 2000 we started this particular work, like how to make input-output modeling, okay, for the grinding operation. Then we carried out input-output modeling on turning operation, carried out on lathe. Then casting, like sand mold casting. Then forming also we implemented laser forming. Then welding, different types of welding we consider TIG welding, MIG welding, electron beam welding. We worked extensively. I think at least 5-6 PhD I guided on this EBW only out of 22. Then laser beam welding, once again 2-3 PhDs I guided, and this EDM, electro discharge machining, plasma spray coating, 1 PhD I guided, then abrasive flow machining, etc. Okay. So casting also one PhD was guided, forming another PhD was guided by me, TIG, MIG, another PhD was guided here. So a lot of PhD thesis was guided by me in the area of this input-output modeling. And in robotics also a large number of PhDs was guided, I think, by me, might be around 8 or 10 in robotics, rest of the things in manufacturing science. And there was one work on medical diagnosis. Okay, this was done by a doctor, one MBBS doctor, he carried out so this particular research. Okay, and once again we tried to find out the input-output relationship related to mental disease, that is psychosis. So we consider 24 symptoms as the input according to BPRS F2 manual available in the medical science. Okay, and we also collected data with the help of 40 doctors. We did the screening of the patient using some clustering algorithm, fuzzy clustering algorithm, and then the level of the disease was predicted using the fuzzy reasoning tool. So it was a problem of screening and prediction. And we use clustering as a screening tool and fuzzy reasoning tool as a prediction tool, so that as if we tried to model the knowledge base of a medical doctor, the expert medical doctor in the field of psychosis or mental disease. The moment a new patient is coming, so the doctor is going to ask a large number of questions, and depending on the reply or the answer he gets from the patient, he is going to do some sort of classification and some sort of screening and classification just to identify whether that particular patient is suffering from mental disease or not. And if he suffers from the mental disease, then what should be the grade of that particular disease? And accordingly, the medicines will be prescribed. Okay. So according to that BPRS F2 manual, there are 7 grades of your mental diseases. Okay. That is schizophrenia, mania, depression with psychosis, delusional disorder, schizoaffective disorder, organic psychosis, catatonia. So these are the 7 classes of mental diseases. And using that particular data, we could do a very good clustering also. You can see that each of the clusters belongs to a class of mental disease. You can see there are 7 clusters here, like 1, 2, 3, 4, 5, 6, and 7. You can see a very good clustering, okay, or the classification of that particular, the 7 grades of mental diseases. Okay, and once you get this, now this input output modeling, that means the patient is going to share his experience of the experienced doctor. Okay, and the doctor is going to do some sort of screening and prediction, and accordingly the medicines will be prescribed. So this is done by the doctor as if we are trying to model the knowledge base of an expert medical doctor. Okay, this work actually, this PhD work I guided long back in 2005, 2006. Okay, so these are all applications, and there are many applications which is solved. So much time is not there. So related to manufacturing, a lot of problems we solve, particularly electron beam welding. We consider the welding of similar material, dissimilar material, reactive material, okay, and different types of special types of material. So their weld defects and other things we model. Their microstructure, metallurgical properties, mechanical properties we measured and did the modeling. Okay, for example, how to minimize the welding defect so that we can select the input parameter to minimize the oil defects and all such things. Okay, and with this discussion, I'm just coming to the concluding remarks that input-output relationship can be established both in the forward and reverse direction if you want to automate a particular process, we have the conventional statistical regression analysis, which could be very efficient for forward mapping, but it may not be always possible to carry out the reverse mapping. huh? But if you use fuzzy logic based or the neural network based analysis, you can carry out both the forward as well as the reverse mapping, and you'll be able to establish the input output relationship both in the forward as well as in the reverse direction. Now, as I told, these are the references. Several times I mentioned about this textbook on soft computing fundamentals and applications written by me. Then NPTEL course, traditional and non-traditional optimization tool developed by me. So this is the site, okay. Then NPTEL course on fuzzy logic and neural networks developed by me. This is the sites, okay. And there is another NPTEL course on robotics, which is running now, I think almost at the end, and it will be rerunning from July 2021, okay. And the NPTEL course on traditional and non-traditional optimization tools and fuzzy logic and neural networks will be rerunning once again from this January, February 2021. I think the registration has already been started, and if you are really interested, you can also join this NPTEL course. And as you know, this registration fee, it is free of cost. Okay, it is the Government of India initiative, so it is free of cost. So if you are really interested, you can join these NPTEL courses. I think the registration process has been started for both these NPTEL courses now. You can just visit these particular sites, so you'll be getting a lot of information, like how to do the registration if you are really interested. Uh, is there any doubt here? Anything? No. Okay. These are the books which I've written. Some of the books, soft computing. Then this is the Chinese version of soft computing, the robotics book. This is analytical engineering mechanics, because I'm basically a mechanical engineer. These are all edited books and the research monograms and all such things. Okay. With this, I thank you. Thank you very much for your patience. Actually, in short time, I covered many things. I tried to tell you the philosophy behind going for this type of analysis, but detailed mathematical expression and all such things are available in the NPTEL lectures, which is also freely available in YouTube, and it is also available in the textbook written by me. That is why very purposefully I did not go for the mathematical expression, because I wanted to give you some initial momentum sort of thing, so that you can start thinking on this particular area. And if you are really interested, you can learn more by concentrating on my NPTEL lectures or my textbook. Okay. So I just tried to give you the overall picture, the way the input-output modeling is going on to solve a variety of problems related to not only engineering science. Nowadays, these are used in general science, physics, chemistry also. Particularly in chemistry, there is a lot of application nowadays. Okay. Then you can even use in art subject, law-related subjects, finance-related subject. Okay. So these principles can be used everywhere. These are all multidisciplinary work. Okay. With this, I thank you once again for your patience, and for giving me the opportunity to share my ideas. And now, if you have any doubt, I'll try my level best to clear your doubts. So the doubt clearing session starts now. You can start asking some queries or questions if you have. Yes, anybody who is having any doubt?
Participants, if you have got any queries, you can ask.
এই ফ্যানটা একটু বন্ধ করে দেবে গো? শুনতেও পাচ্ছি। Yes, any doubt? Anybody?
Participants, if you have got any queries, you can ask. So, sir, I think there are no doubt, no queries for you.
Okay, okay, good.
Thanks, sir, from
Ah.
our department, our institutions. I am Professor D. Mishra, who is the coordinator of this program, particular FDP.
Okay, okay, Professor Mishra, thank you.
So I extend my hearty thanks to you, and I hope that in future also we'll show the same gesture, and will require your.
Okay, I'll try my level best to help.
So thank you again, sir.
Okay, okay, you are welcome, very much welcome. Now this PPT, do you need the PPT?
Yes, many participants are asking for the PPT. So if you allow, you can share this PPT. Send this one, sir.
So I think you can take it now from there.
Yeah.
Can you take it?
No, we cannot take it from here.
Okay, then I'll do one thing. I'll make a PDF of this because it is having big size. Okay, so
Okay.
I'll be doing the PDF and try to send you the address of Professor Mahapatra. Okay.
Okay, sir, that will do.
So might be I'll be sending from my IIT Kharagpur email or from my Gmail. Okay, I'll be doing that. Okay.
Okay, sir.
Okay.
Thank you, sir.
Okay, thanks a lot. So I'm just going to disconnect now. Okay.
Okay, sir. Thank you.
Okay.